Duyuyor musun şu anda?
Merhaba, sesim geliyor mu?
Evet, geliyor. Aykut'un sunumunun başlığı Simple Instructions for Ethereum Virtual Machine. Aykut, biraz önce bahsettiğim gibi 15 dakika süremiz var. Ona dikkat edip sunumunu yaparsan çok seviniriz. Başarılar şimdiden.
Teşekkür ederim. Our topic is Simple Extension for Ethereum Virtual Machine. The presentation outline goes like this. I will first start with background, and then I'll state problem and our contribution to it. Then I will show related works, our methodology, and then experiment and results. And at the end, I will conclude and discuss what can be done further. As many of you know, blockchain is a distributed database. The difference from other databases, it is immutable. It stores immutable data in its blocks, which are chained into previous blocks. The immutability is ensured by the cryptographic hash function and also consensus protocol. Cryptocurrencies are based on that blockchain technology. Bitcoin is the first representative of cryptocurrencies, and it is called blockchain 1.0 technology because Bitcoin only allows money transfer transactions. On the other hand, there are also blockchain 2.0 type of cryptocurrencies. They are also allowing smart contract transactions besides money transfer transactions. Smart contracts are like any other personal accounts. They have address stored on the blockchain. Besides the address and balance information, they also have immutable code and mutable data stored on the blockchain. For example, any real-life logic such as trading on a house could be encoded in a smart contract, which is deployed on the blockchain 2.0. Ethereum is one of the most popular representative of those type of blockchain. It allows both money transfer and smart contract transactions. It does this with the help of its virtual machine, which is called Ethereum Virtual Machine. It is a Turing-complete machine, and it interprets Ethereum bytecode. It has two types of states. One of it is persistent word state. In this state, it stores all information about both personal accounts and also smart contract accounts. It stores code information, balance information, and mutable data information for accounts. In volatile state, it fetches the code from this persistent word state and store it into a mutable code area in memory, and it executes those instructions on the virtual stack area, and it uses some virtual registers as well. Program counter register stores the next executed instruction, and available gas register stores the left amount of gas for the current transaction. Ethereum has a concept of gas. Each transaction is sent with an predetermined gas, which is sent by the transaction sender, and also transaction sender put the gas price for a unit gas cost. Ethereum made this concept because they wanted to deal with the problems of halting and DOS attacks. First of all, when a transaction is executed, the gas amount sent by the transaction sender put into the available gas register, and also every instruction in Ethereum virtual machine also is assigned a gas amount. When the transaction is executed, the available gas register is reduced by the gas amount assigned to the instructions. And if the available gas hits below zero, the transaction is aborted. With this concept, they prevent problems of halting and also try to prevent those attacks. We address two types of problem in Ethereum. It is gaining immense popularity recent years, and its load getting higher and higher, and it needs to scale better. is transaction throughput should be implemented some way. And also blocks have gas limit, and because of that, some smart contracts consuming a huge amount of gas. So blocks cannot include as many transactions as they want. They are limited by that gas limit. And we try to increase the transaction throughput and also reduce the gas costs for data parallelizable transactions by using SIMD instructions. With SIMD instructions, we can execute more than one operation with just one instruction by putting many values into large registers, and just executing one instruction, we can handle more than one operation actually. By employing this strategy, we can speed up and reduce gas costs for data parallelizable algorithms. An example of vector addition by using scalar operation in Ethereum virtual machine. For example, if we are adding two vectors of size 8, we are doing this one by one if we are using scalar operations. For example, for the first operation, we are pushing the first elements of both vectors and adding them. Stack state looks like that, and we are doing the same thing for the second elements as well. We are pushing the second elements and adding, and we are doing this for all of the elements one by one. At the end, stack state looks like this. Totally, we executed 8 different addition for 8 elements. If we are using SIMD instructions, we can do this with just one addition. We can push the whole vector elements into the stack item, and then we can push the other vector element onto the second stack item. Then we can add them with just one operation. Actually, each stack item has a width of 32 bytes, so we cannot overflow this value. We are considering this. I will mention next sections. Actually, our works is based on some Ethereum improvement proposal, which is drafted by Greg Colvin in 2017, which is in stagnant status. We based our works on this Ethereum improvement proposal. And also there are different types of studies using SIMD instructions and get some different boost ups. For example, SHA-512 got 7x and Blake 2B got 4x speed up. And others similar optimizations are obtained for cryptographic functions. Our methodology is extending C++ implementation of Ethereum virtual machine interpreter, which is called ALET. You can find it on GitHub. And we used some generic SIMD library to extend this implementation. It has very good, nice fallback options, which means if some CPU does not support any SIMD instructions, it just fallbacks to sequential mode. So we did not deal with the support for different types of SIMD architectures. We design our opcodes as 2 bytes. The first byte encodes the operation code, just like any other current instructions. We used an extra byte, second byte, to encode the SIMD-related information. As you can see from the table, the first byte is similar to other opcodes. It's just encodes the operation code. The first bit of the second byte encodes the operation type. It is either integer or floating point. The middle 2 bits encodes the operand width, which is called lane width. The last 3 bits encodes the lane count, which is the operand count one SIMD instruction can operate on. The SIMD instructions we have added looks like on the table. We have added 16 different types of SIMD instructions, which contain arithmetic comparison, bit and push operations. We have assigned some gas those operations, which will be seen in the next slide. While assigning gas units to those instructions, we have used this idea. We know that a no jump test instruction takes approximately 20 cycles for CPP ALET, and it is assigned a cost of 1. And then we have another measurements for SIMD instructions with operands with less than 8 bytes. It takes 20 to 30 cycles, and then we assign this 1 gas unit because of we are basing the jump test cycles. And 16 bytes operation approximately takes 30 to 8 cycles, so we assigned 2 gas units. And with the same idea, we assigned 32 bytes operation 3 gas units. For all operations, it takes similar cycles, except division and mode operations takes approximately 5 times more cycles, so we assigned them 5 times more gas units. And because we did not have any compiler support for SIMD bytecode generation, we needed to create a basic small SIMD bytecode generator. It converts human readable instruction format to bytecodes for SIMD operations. An example execution like that, we are giving it a simple input file in human readable format, and it generates the bytecode related to it. Actually, I did not mention something, but I will mention it now. Okay. I will show experiments and results. We have benchmarks for all possible operand width and for all possible lane count combination. Because stack item width for EVM is 32 bytes, we could not overflow it. So for each lane width lane count combination, lane count multiplied by lane width should not exceed the 32 bytes. We considered this. And for each benchmark case, we computationally compute 3,200,000 scalar operation. And on our CPU, we used AVX2 and 16 GB of memory on Linux. And we can analyze the execution time benchmark results. We benchmark for all type of operand widths, which is called lane width, which are 1 byte, 2 bytes, 4 byte, or 8 bytes. And for each lane width, there are possible lane counts. For example, for lane width 1, we can at maximum make lane count 32. But for lane width 2, we can make the lane count at maximum 16. We cannot overflow the 13 bytes of EVM stack width. So as you can see here, while we are increasing lane width, the execution times are increasing as well. And while for each lane width, while we are increasing lane count, x-axis is lane count, we are increasing it by 2 times, and the execution time approximately decreasing by 2 times. Because we are doing the same computation with just less amount of instruction using SIMD. And our gas benchmark looks like this. Again, we have benchmark for all type of lane widths and lane counts, possible lane counts. After assigning the gas costs as described by previous sections, we can see that while we are incrementing lane count by 2, we are also reducing the gas costs approximately by 2 for all type of lane widths. I will conclude and discuss what can be done further. We have added 16 different types of SIMD operations to the EVM, and we approximately obtained 3 to 14 times cost reduction and also 3 to 9 times speed up approximately for vector operations. we obtained portability with the help of generic SIMD library, which is called libsimdpp. It has nice fallback options, as I said before. We had some disadvantages because we had no native compiler support. We have written our compiler, basic compiler, so we could not generate more realistic benchmark inputs. We just repeated the same vector operation again and again. So this is not so realistic, but gave us some idea. Another thing, we can add more complex SIMD operations like reduction and shuffling. And also we only considered data parallelism. Maybe we can improve Ethereum virtual machine with other parallelism models like pipelining, maybe thread-based parallelism or something like that. And thank you for listening. If you have questions, I can answer.
Any questions from the audience? No questions? Okay, and I want to thank you one more time, Aykut. And we are going to move on our last speaker. Our last speaker is Buse Yılmaz from İstinye University.
Thank you. So hello, I'm Buse Yılmaz from İstinye University Software Engineering Department, and I will be talking about a graph transformation strategy for optimizing sparse triangles over multiple machines. So SPTRSV is an important building block in of sparse linear algebra systems such as iterative methods, preconditioners, or least square problems. And on the right-hand side, we're seeing the operation performed. It's a forward substitution in Gaussian elimination. And we have the lower triangular matrix L, which is sparse, and we multiply it with a dense vector X when we end up with a dense vector B. And then unknowns here are the contents of the X vector. Optimizing SPTRSV is not trivial, especially on today's highly parallel architectures, due to the challenges that is posed by this sparse pattern. First of all, it's non-uniform usually throughout the matrix. There are some parts of the matrix which exhibit very little parallelism, such that the computation is almost serial, such that your cores are sitting idle at the side and you're not taking advantage of the parallel architecture at hand. Of course, this causes significant load balancing problems. Dependencies between computations manifest limited parallelism, and computations are quite irregular actually, and they vary in granularity. So this causes significant synchronization overheads. There has been a very successful several works in the literature, and usually majority of them are based on partitioning the matrix into smaller pieces and solving them with the appropriate method and or on the appropriate architecture. In a previous work, we took exactly the opposite approach, where we're trying to increase the sparsity pattern, the parallelism of the parts where they lack it. And we realized this using the equation rewriting method. And in this work, we're presenting a preliminary algorithm for the equation rewriting method. So what is equation rewriting method? So on the left-hand side, you're seeing the dependency graph of the matrix, which is partitioned into levels by level set method. Level set method is a well-known method which is used for the SPTRSV, where you have the rows grouped in levels, so you can compute them in parallel because they don't have any dependencies between each other. But you have the consecutive levels, which are computed in a serial manner, and they're separated from each other using synchronization points. And in this graph, the nodes are representing the rows, and the integers are representing the dependencies between the computations. For example, to compute row 7, you need to compute row 0, 3, and 6 prior to that. In the middle graph, you're seeing the rewriting equation method applied to row 3. We're breaking the dependency of row 3 to row 1, and we can shift row 3 to level 2 from level 3 using this method. What is the operation performed? If you look at the original equations, look at the equation of x3, and we simply replace the x1 there with its original equation, which is indicated in blue. That's what we do as rewriting. If we continue applying this method, we come to the graph shown on the right-hand side. This time the operation is in yellow. So we take row 3 and break its dependency to row 1, and we can move it to level 1 now. So level 3 is now empty, and we can remove it altogether, meaning that we're shortening the critical path of the graph. Also, we're removing one of the synchronization points. And we end up with this long equation at the very end after performing these two operations. And you can realize that it's not in LX is equal to B format anymore. It needs to be rearranged. After we rearrange that, it's going to look like the original equation of x1, which is also in the level 1. Well, you cannot see that part very clearly, because sorry about that. It doesn't have any dependencies, so that it is in level 1, and it is a very short equation. So, of course, there are endless possibilities when we think about graph transformation, especially if the number of rows to be rewritten to other levels increase, these possibilities grow exponentially. There are two major aspects for graph transformation using the rewriting method: rows to be rewritten, source levels, and levels to which the selected rows will be written, the target levels. Of course, there are other aspects to be taken into consideration. First one is the stopping criteria. Technically, you can rewrite all of your rows to the level 1, but it's impractical and it's meaningless. So you need a good stopping criteria. Another one is the transformation cost. You need to keep it low so that it is reasonable, because transformation cost plus your algorithm, SPTRSV algorithm applied on a transformed graph, should still be able to provide us performance gains. Lastly, we're after reducing the critical path, so we want to reduce the synchronization points, and the key to that is to use the rewriting method and empty some levels. For the major aspects and the stopping criteria, we use the average level cost. I'm sorry if the red one is not really visible to you. So that's average level cost. So if a level's cost is smaller than the average level cost, that means it's a thin level and it's a subject to the rewriting method. So we select both the source levels and the target levels from the thin levels. And also we use it as a stopping criteria. Whenever a target level's cost reaches to the average level cost, we can stop there. So what is the cost of a level? It's the sum of the cost of all the rows. So what is the cost of the row? It is the arithmetic operations performed to calculate this value. For the transformation cost, to keep it reasonable, we select the source levels as close as possible to the target level so that we can increase the locality. And to reduce the synchronization points, instead of rewriting individual rows, we rewritten whole thin levels so that we can empty some levels. In the slide, you're seeing the pseudocode of the algorithm on the left-hand side, and there's a small example on the right-hand side. So first of all, this approach requires us to know possible cost of a row at each level between the source level and the target level. That's what we do. We calculate a row's possible cost at each level up until we reach to the target level. On the right-hand side, we're assuming that the average level cost is 22, and we have 4 levels. And the initial setup is shown with the columns rows. And we build up a cost map using this algorithm. And the red ones indicate the cost of a row. For example, row 0 has cost 1 and row 1 has cost 1 and so on and so forth. So since the average level cost is 22, we can, when we calculate the possible costs of row 2, 3, and 4, it makes up 21, which means we need to stop there. And the next target level becomes n+2, since n+1 is now empty. That's how the algorithm works. Selecting the average level cost as a stopping criteria was reasonable and natural at first, but we realized that it poses some problems. It can cause long rewriting distances, especially if the cost of the source level is very small compared to the cost of the target level, or if the rewriting method doesn't increase the cost of a row, which happens because sometimes the number of the dependencies don't increase. Long rewriting distances are observed. Of course, in turn, this increases the rewriting cost. And it can also pose some precision problems because now you're forming long computational chains. Also, a divergence between memory accesses can be observed because while rewriting, you're changing the dependencies, even if you're increasing or decreasing or not changing the number of dependencies. Another limitation that can be talked about is the rewriting entire levels. Since we're rewriting entire levels, actually we're missing out on the opportunities when we will be rewriting individual rows, and I have some examples of those here. Lastly, architecture dependent features are not taken into consideration in this algorithm at all. So let me move to the experiment results. We chose 2 real-world matrices from Sparse matrix collection. These are both square matrices. One is around 400K non-zeros, and one has 1 million K round non-zeros. So we're talking about a rewriting method and its implementation, and we need an underlying SPTRSV implementation to use a transformed graph. So for that, we use our own implementation, which is a code generation framework, but it's still under development. So it is barely working, let me say. So that's why I won't be presenting any runtime values, but I will be comparing it to a previous approach that we worked on. So before I dive into the details, let me talk about what is this previous approach. It is indicated with the yellow one, which is called manual approach. In the manual approach, the programmer selects the rows to be rewritten, also the target levels, and every 9 level is rewritten to the 10th level. So as you can see, it is completely blind of the underlying sparsity pattern. Okay, so we compared our approach, which is in blue, to the yellow one, the manual approach, and also we compared these two to the no rewriting case. So no rewriting happens in that case, which is indicated with green. These are the results for lang2. Lang2 is an interesting matrix. It has 94% of its levels only having 2 rows. So that long neck is quite serial. So our goal is to squeeze this matrix by rewriting the rows to upper levels. If you look at the number of levels, you can see that our approach decreased the number of levels by 95%, whereas in manual approach decreases by 86%. And number of rewritten rows follow a similar trend. But if you look at the total level cost, we see that there's a very slight decrease in both of the approaches. The reason is that it is threefold. First of all, we're rewriting some rows to the top level, which makes this cost 0 because now they don't have any dependencies. Second, for lang2, due to the sparsity pattern, the number of dependencies are not increasing. They're not changing at all, actually, when we're rewriting them. And third, while we're rearranging the equations after rewriting them, we can remove one of the computations, the division operation. That's also helping with the reduction of the floating point operations needed in total. Torso 2 is quite different compared to lang2. It has majority of its levels having close number of rows to each other, and their costs are close to each other. So that actually resulted in fewer number of levels to be rewritten. as opposed to lamp 2. And since also it's a bigger matrix, we are observing that number of written rows increased compared to lamp 2. If we look at the total level cost, we see a very slight increase in the total cost with our approach, the blue one, whereas the manual approach is just went off the charts since it is completely blind on this sparsely pattern. I think, excuse me, I think that slight increase is still reasonable. So to conclude, in this work, we are presenting an automated preliminary algorithm to transform the graph for optimizing SPTRSV on multi-core machines. What we have done is that we thickened some of the levels so that so those levels are lacking parallelism, so they became more parallel. They became thicker levels, and we decrease the critical path of the graph so that we remove some of the synchronization points. Now we would like to develop a more sophisticated algorithm incorporating the limitations that we have discussed and also more criteria. Obviously, these are not enough. And that will be all. But before I finish up, I'd like to tell you that this work is supported by SPTRSV. And I still have open positions. And if you're interested, please do not hesitate to contact me. And that will be all. Thank you for your time.
Questions? Thank you one more time.
Thank you very much.
That will be the end of today's session. Now I think we have a